Hello students, here we are going to learn about RWE architecture variations, routing and wavelength assignment. So one of the set light path has been chosen or determined. We need to route each light path in a network, in the particular optical network. So assign a wavelength to it. This is preferred to as a routing and wavelength assignment problem. So the problem considerations a set of light path that need to be established on the network. So a constraint on the number of wavelength also. So case of determine that the routes over which this light path should be set up, and the wavelength which should be assigned to the particular light path, or light path is blocked when cannot be set up due to the constraints on fiber, or in case of wavelength. So the corresponding network optimization problem is to minimize the blocking probability. So also the cost optimization problems and the provisions that the set of light path using a minimum amount of resources. So start with the first relation to the graph coloring. So in this case, relating to the graph coloring, the objective is assign wavelength or wavelength terms of the color to each light path so as to minimize the number of wavelength used under the wavelength continuity constraint, and also construct a graph G so that each light path in the system is represented by a node. So undirected edge between node in the particular graph G is corresponding light path share a physical link, and so color the node in the graph G such as that a node to adjacent node have the same color using the particular graph coloring. So how to construct a graph? So in this case you construct graph G bracket V or E. So each light path in the system represented by the node in graph G. So there is an undirected edge between the two nodes. Their corresponding light path pass through a common physical fiber link or common dedicated link between them. So the color the node of the graph G such that not two adjacent node have the same color. I'm also explaining. So this problem has so the NP complete. So this is the minimum number of color needed to the coloring of graph particular G is difficult to determine. So there are efficient sequential graph coloring algorithm is there to design such kind of graph coloring. So offline RWA maximum load model. So this corresponding to the static network design problem, where only a single set of light path to be supported for the each kind of a node is connected between the input and output for the particular network. So this set is constrained to be such that it can be supported in a network with node capable of full wavelength convergence with at least most L wavelength per link. And since that particular in the network, the routing that place no more than L routes on any link. So they provided the particular dedicated provider. So the maximum load for this set of light path is said to be L or capital L already defined. So in a network with the node incapable of wavelength conversion, so more than L wavelength per link would be needed. So in general to support the same set of light path. So determine the additional number of wavelength that would be required to support every set of such light path with the node. They do not have any wavelength conversion capability or the capacity. So according to that, some of our point is given in this point. So starting with the first, given a routing of a set of light path with the load L in a network G with provided the capital M edges. So with the maximum number of hop in the light path being a capital D, so number of wavelengths sufficient to satisfy this request. So particular request is given. So for that, this proof of this particular equation is that, so we have observed that each light path can interest with the almost, I'm writing down over here, L minus 1 into capital D other light path. So therefore the maximum degree of light path provided the particular path or path graph is known as L minus 1 into D. So any graph with the maximum degree delta can be colored using delta plus 1 color by simple greedy coloring algorithm, and hence the path graph can be colored using also L minus 1 into D plus 1 colors. So next, suppose we are giving a request of source destination pairs and the maximum possible load for satisfying this request is L min. So the shortest path routing yields a load of most 2L min. So the for this case, shortest path routing. So consider as a shortest path routing. I'm just giving a notation like the over here. LSP, shortest path for routing. So consider that the one link is I. Consider as a one link is I with load LSP. So shortest path routing. So rerouting K connections, considering the rerouting possibility using a K connections, using a particular link I are routed on the path, or in case of length is always, this length is always less than or equal to square n divided by 2. So initially in their case of a longer route on this ring, we'll use the particular link n by 2 plus 1, sorry, plus I. So this is a maximum or longer route provided by Joe. So increasing its load by the particular K. So increasing particular load by K. So therefore the load L mean, so that this particular request L mean of the optimal routing algorithm must satisfy the following condition: L mean greater or equal mean K and maximum possibility of LSP the routing path minus K comma K, yeah, or L mean greater than or equal to LSP divided by 2. So third one, given set of light path request and a routing on a ring with load L, so WANC can be done with 2L minus 1 wavelength. So this particular thing determines that the node in the ring with the minimum number of providing, I'm also explaining the one path passing through it. So the particular consider that the interval graph with the maximum load of L, capital L. So which can color with the how many number of wavelength? So L number of wavelength. So using a particular mechanism to deal with the L light path that may wrap around the edge of the particular things or the line. So we can always design a wavelength to this light using a L additional wavelength provided that requiring a total number of L plus 1 wavelength. So fourth one is consider a ring network that has full wavelength conversion at one node and no wavelength conversion at other node. So this network can support all light path requests with the load L less than or equal to the capital W. So in this case of a limited wavelength conversion can help us significantly in improving the load, so that can be supported in many network configurations, and the detailed derivations of the result for this case are beyond the scope. So we can consider that the particular path is provided in the particular ring network in this case also. So starting with the next topic, online RW with the maximum load. So in this case, the routing of the light path is already given, and that the light path are set up as well as taken down, and that is the light path are non-permanent in the particular network. Clear? So here it become much more difficult to come up with the smart algorithm. So that particular the minimize the load that can be supported for the networks without full wavelength conversion. Clear? So it is assumed that the routing of the light path are non-permanent and without wavelength conversions. So the algorithm to provide efficient wavelength assignment. So from for that some of considerations are given. So let us consider one by one. So first is consider W and L, the number of wavelengths needed to support online light path request with the load L in a network using n number of node with the no wavelength conversions under this condition. So this condition is given where n is a power of the 2 factor. So this particular line network is the middle to realize two disjoint subline networks. So each with n by 2 node provided by n by 2 node. So the break the set of light path requests into the two different group. So one group is a consist of the light path that entirely within the subline networks, and consider for the another group for consisting of light path that go across between to the subline networks. So the former group of light path can be supported at most of the particular W n by 2 L wavelength, and this particular set of wavelength can be used in the both subline networks. And the particular thing that the light path can have load of most L and dedicated L additional wavelength to surviving this group. So this is proof of this particular point one. So point two, in a line network with n node, online light path request with load L can be supported using the most L log to n wavelength with no wavelength conversion. So this algorithm provide to implied by this theorem is quite efficient, and it is possible to come up with the light path traffic pattern for which any algorithm is required. So at least they provide log to n, so at least 0.5 log to n wavelength. So third is in a ring with the n number of node, all online light path requests with load L can be supported using the most L log to n plus L wavelength with no wavelength conversion. So when we have the permanent light path being set up, so it is possible to obtain somewhat better wavelength assignment to particular providing this particular kind of network with the n node and the load and supported the particular wavelength with the no wavelength conversions. So in the fourth, in a ring network with the n node, all online permanent light path requests with L node. So L node can be supported. So there are two cases explained: the at most 2L wavelength with no wavelength conversion, or with almost maximum load like that 0L minus D plus L wavelength with the degree of particular limited wavelength conversion. So there are two cases available over here: no wavelength conversions and the limited wavelength conversion. So in this case, the number of wavelength required in the ring to support all pattern with the maximum load L for the different models. So in case of offline and online, so the particular small d available over here denotes the degree of wavelength convergences. So in this case, there's no convergence is provided, but in the case B, convergence, wavelength convergence is provided. So this is a degree of wavelength convergence. So the upper bound apply over in case the particular point. So number of wavelength that are sufficient to accommodate all the kind of traffic pattern with the maximum load L using a RWA algorithm. So the lower bound index is that the sum of the traffic pattern with the maximum load L that requires many wavelength regards of the RWA employed over here. Clear? So the next point for online RWA statistical model. So in this case, there are the basically two kind of statistical traffic model can be used to solving the dimension line problem, or this kind of problem is generated to this RWA. So for that, these models different their assumptions regarding what is known about the set or the set of light path that can be supported. So first is a first passage model. So in this model, network is assumed to start with the no light path particular, and the light path arrive randomly according to the statistical model and have to be set on the particular optical layer. So some of the light paths may depart as well as, but it assumes that the average number of light path will keep increasing and eventually will have to reject the certain light path request also. Second is a blocking model. So in this model, the light path requests are considered or treated in the same way as the telephone network, or the treated as a telephone calls network. So the request assumed to arrived and depart at the random instant according to the statistical model. And this assumption is most requests must be considered as some of the requests may be considered as a block. So for that RWA problem using a statistical model for the traffic, so it is assumed a fixed route between each source destinations pair, and present some simulation results to show that the effective of alternate route also provided. So the consideration of the 4 RWA parameters over here. So first is a random one. So for that, get the light path request between two nodes. Choose at random one of the variable wavelength on fixed shortest path between these two nodes. Random 2, fix two shortest path between every pair of node. For a light path request between two nodes, consider at random available wavelength on the first shortest path, and if no wavelength is available, so choose a random available wavelength on the second shortest path. So next one is max used one. So in this case, for light path request between two nodes among the available wavelength on fixed shortest path between the two nodes, and choose the one that is used the most number of times in the network at the time of a particular time. And last one is max use 2. So first two shortest path between every pair of node among the available wavelength on the first shortest path between two node, choose according to one that is used most number of times in the network at that point of time. So if no such wavelength is available, so choose the one that is used the most number of time in the network at the point of. So here I'm just explaining some figure over here. So consider as a 120 node and 32 link network representing a skeleton of the particular network. So an average of one line path request is assumed to arrive month between each pair of node, and this light path assumed to be placed for average of 1 year. So the topology considered over here is a 20 node and 39 links. Okay, so consider 32 wavelength available on the each link that the traffic is uniform. So the reuse factor obtained by using each of above 4 RW algorithm for blocking probability. Consider over here I am also random 1, random 2, max as used 1, max as used 2. So the blocking probability of 1% consider in the particular table. So this is that the reuse factor improves substantially when an alternate path is considered. Ideally, we have a more alternate route for a longer route and a few routes for the shorter route. So this will have to reuse a blocking probability on a longer route ensure for the better for the all over the networks. Shortest route tends to have much less blocking than the longer routes. So having a more route to consider usually increasing the traffic in the network and leads additional computation burdens on the network node. So here consider 20 node, but this is not a significant in the network with the moderate number of nodes where light paths are set up and takes down slowly. So here is the reuse factor is for random one is 6.9, 7.8 for random 2, max use one is a 7.5 and max use is a 8.3. So reuse factor for 1% blocking in different RWA algorithm for particular 20 node network consider over here.